Okay, so we're doing chapter 5, atomic theory. What was that? Let me see. So you need a folder, right? Is that you're telling me? Or a binder? Don't worry, I got something for you. Remind me to give it to you afterwards. Okay, so chapter 5. Everybody's read it. I don't really need to go through it, right? So I can just start asking questions and we'll see where we get. No, no. What do you mean, no? Did you get in officially? Okay. So do me a favor, stay after, we'll take a look. Okay. After class. Okay. So, what was that? You can sit there. If they're not there, then it's you. Okay, so there's this guy named Dalton. Dalton has this theory based upon the atom, right? And so what he said was that each element is made up of individual particles called atoms. And these atoms are indivisible. Do you guys know what I mean by indivisible? It means it can't be broken down. It can't be separated. Okay. So an atom can't be separated. That's what he said. Then he said that all atoms of one element is, can you guys see my little hand here? One element is exactly identical in every way. Every way. And then he said that atoms of different elements, atoms of one element are different than atoms of another element. Okay, so that basically is kind of like saying, oh, carbon and oxygen are different, right? You can kind of agree on that, right? Okay, good. So, and then he said that atoms can be combined to make compounds, right? So they can be combined in different ratios to make compounds. So we could get carbon dioxide or we can get carbon monoxide, okay? Now, I want you guys to sit there and take a minute and listen to the lecture. And then I want you to think about which one of these are full of crap, okay? Which one wasn't true? Because it's a theory, that doesn't mean that it's true. There are parts of it that could be wrong, okay? So we're gonna go through the lecture and then I want you to, as soon as you start figuring it out, you let me know, okay? Is that fair? Promise? Okay, you gotta be adamant too. You can't be, oh, I think it's, you gotta be, oh no, I know it's this, right? Okay, I'm holding you guys to it. You ready? Okay, here we go. So, just to kind of remind you so you don't forget what we talked about. So, Dalton says, hey, look, there's these atoms, right? And they're all exactly identical, right? For one element, they're going to be exactly the same. So this oxygen is going to be looking exactly like this oxygen. They're not going to differ in any way at all, okay? Not mass, not any way. And so he basically showed us this, you know, hey, elements that are identical are going to weigh exactly the same, right? If they're the same elements, it's going to be exactly the same weight, same mass. But if they're different elements, they're going to have different masses associated, different properties. Atoms can't be created or destroyed. And then we can put atoms together in different ratios. Okay. Having a little trouble with my computer today. Doesn't want to. Okay, that'll work. So, law of multiple proportions. Law of multiple proportions basically says that when you have two atoms and you combine it to form a compound, that ratio for that atom is going to be kind of given. So, like for instance, for carbon dioxide, we have 2 oxygen for every 1 carbon. For carbon monoxide, we have 1 oxygen for every 1 carbon. And those 2 guys are not going to behave the same way. Carbon dioxide is quite different than carbon monoxide. Carbon monoxide, if it has oxygen present or anything like that, could kill us because it's poison, right? Carbon dioxide, we actually breathe out, right? So, and regardless of whether this is on a particulate level or a macroscopic level. What is the difference, particulate and microscopic? Yes, sir. That's right. Macroscopic. Okay, so regardless of whether we can see it with our naked eye or whether we can see it, we can't see it, we can only see it. Specialized microscope, that ratio is still going to be the same. Okay, so that's what the law of multiple proportions. Okay, so I'm going to introduce you to electrons. So electrons are subatomic particles. So subatomic basically means smaller than the atom, right? And they have a negative charge associated with them. Okay, so they're negative. Okay, they have a -1 assigned to them. Also, electrons weigh so little that they're 1,837th of the mass of a hydrogen nucleus. Hydrogen nucleus is just basically a proton. Okay, so let's kind of put this in perspective. So if I put a speck of dust on my shoulder, I weigh 220 pounds. That's going to change the amount that I weigh? No. Okay, so an electron weighs a speck of dust on a proton. Okay, yes, sir. Well, so in other words, an electron is going to affect the behavior of the atom if there's more than what there should be. Yes, yes. And we'll get to that. Give me an opportunity to get there. Okay. Okay. So now the electron was basically discovered by J.J. Thomson. Now, J.J. Thomson basically had said, okay, yeah, there's these electrons and they're negatively charged. He was right on that part. But he also said that the atom is just this mixture of positive and negative charges. It's all mixed up like a pudding, right? Specifically, he said a plum pudding, right? And and so plum pudding just basically means that it's all nicely mixed all together. Well, then Rutherford comes along and he says, hey, JJ, you're wrong, right? There's some order to it. There has to be some type of order associated with it. So what Rutherford did, he basically did an experiment. He did an experiment where he took a gold piece of foil and he shot it with positive alpha particles. Alpha particles are positively charged. And so what he saw was that some of these alpha particles deflected, but the majority of them went through, right? Now, positive, I'm putting something positive. How's it going to deflect? Why would it deflect? If I put two negative charges together, what happens? They repel. So then it causes a deflection, right? So what do you think if I'm putting a positive and a positive together, what's going to happen? It's going to reflect, right? Okay. So that kind of means that, wait a minute, hold on. Most of them are going through, but there's this area that there is deflection that occurs. And he saw that it was kind of uniform. So that basically means that, hey, there's this positive center, but you have this negative outside that allowed things to kind of pass through, right? So, and it's a big old cloud, okay? So from this, we've kind of established what we call the nuclear model. Okay, so the nuclear model basically says that, hey, you got this center, right? This mass in the center. And then you have this cloud on the outside. So in the center, you have the nucleus. The nucleus is composed of protons and neutrons. Okay, I haven't introduced protons and neutrons. Let's talk about protons and neutrons. So protons, protons are positively charged. So it has a +1 charge that's going to be associated with it. And the symbol that we use for protons is P superscript plus. Neutrons, that's a P, and that's a plus. P plus. Are you making fun of my 3rd grade handwriting? Neutrons are neutral. They have a 0 charge associated with them. The symbol that we're going to use for that is going to be N0 or N0. And then we've already talked about electrons. Electrons are charged. What's the charge on electrons? Okay, we're going to use E negative, right? I drew that line a little deep there. Huh? I know my head's in the way. You can't see all of it. I'll try to remember that when I make the adjustment. Okay, so protons and neutrons are going to be in the center. They're going to be in the nucleus, right? They're also going to make up the majority of the mass of the atom. Electrons are going to be orbiting around it. So you have this positive center, right? And these electrons that are working their way around it, right? So the electrons are kind of being pulled in by that positive center, right? And that center is really important. If that center isn't strong enough, then it doesn't keep those electrons tightly pulled in, right? The more positive you have, the tighter it's going to pull things in, right? Okay, so this is what it looks like. Here's our nucleus, which consists of protons and neutrons. And then this little blue tint, that's the electron cloud. And so they call it an electron cloud because the electrons are constantly moving, orbiting, all around it, okay? So it kind of gives you an idea. So if we put like a blueberry in the middle of a football field, that's what it's going to look like, right? So the atom representing with the electrons that are running around it is going to be the football field. The blueberry is going to be the nucleus. Okay, kind of put it in perspective, right? Okay, so the alpha particles, they weren't deflected. They only deflected a little bit with that positive charge. And so, but it was very organized, right? And so again, that gave us that this idea of that nuclear model was correct, right? We have that positive center, and then we have that open space that is mostly your electrons that are orbiting. Okay, just a reminder, protons are what charge? Positive. Neutrons are what charge?
Neutral.
Neutral. Okay, good. Okay, so we said that that proton, right? That proton is 1,867 or 1,876. I can't remember, but it's significantly larger than the weight of the electron. Okay, we already agreed that like that speck of dust isn't going to change my weight. So do you think an electron is going to change the weight of the atom? Okay, so the atom is going to be composed of, mostly in terms of weight, it's going to be the protons and the neutrons. That's what's going to make the weight of the atom. Okay, you guys got that? Okay. So if we continue talking about an atom, we need to talk about the atomic number. The atomic number defines the atom, right? So the atomic number 6, right? That tells us how many protons there are. The atomic number are the number of protons. So if we look on the periodic table, this number here in the corner, this represents the atomic number. Now, it defines the atom. It tells us the number of protons an atom has, and that's going to define the atom. It's never going to change for that element. So hydrogen has how many protons?
1.
It has 1 proton because it has an atomic number of 1. Tungsten. Tungsten is W down here. So it has how many protons? It has 74 protons. Okay. Hold on. Okay. So now an element being what it is, it has to be composed of the same amount of positive charges as negative charges if it's going to be a neutral element. Right? So protons are what charge?
Positive.
Positive. And what's negative?
11.
So then how many electrons would tungsten have? How many? 74. Because I have 74 protons, I have to have how many to balance them off? 74 electrons. So we know that tungsten sometimes, we'll get to when they're not. Okay, so we're not going to say always. When we have a neutral atom, right? We have an atom normally off the periodic table, it's going to be balanced. Balanced. Your protons have to equal your electrons. Okay, so protons was 74 electrons. 74. Okay, we all got that, right? Now, this number down here, that number down there is called the atomic mass. It's the mass of the atom. Okay, now I know I heard Dr. Henry say something about the mass. What do you say about the mass? Oh, mass is made up by protons and neutrons. So I can calculate the number of neutrons if I have the mass of the element, right? Oh my gosh, I have the mass of the element. Now, the way it works is that the mass of the element, we're going to take a look at that number. And we're going to make it into a whole number. If that number, this is 8, is a 8 or 5 or higher, then we're going to round up. So then we'll have 184. Okay. So this number, 184, is going to be called our mass number. That whole number that we get is called the mass number. And that's going to be based upon that element. So all we're saying is that we know that it's made up of protons and neutrons. And we know that it's going to be pushed up towards that extra, right? So that mass number is going to be equal to the number of protons plus the number of neutrons. Okay, so we're saying that the mass of one proton is 1. Right? The mass of one neutron is about 1. Okay, so if we add them together, they're going to equal the total mass of the atom that we're looking at. Okay, so if our mass number is 84, put this up. Okay. So if our mass number is 84, sorry, 184, our number of protons for tungsten is how much?
74.
74. So then how many neutrons do I have?
110.
184 minus 74 is 10?
110.
110. Oh, 110. Okay. So we know that neutrons is going to be 110. Okay, see how that works? Piece of cake? Okay, so now I have a hard question for you. Let's go back to hydrogen. Hydrogen has an atomic number of 1. Its mass number, or its atomic mass, is 1.008. So how many neutrons does hydrogen have?
1.
How many? 0.008? What did I tell you? You have to round up. Can you have 0.008 of an atom? If I cut you in many, many pieces, will you still survive?
Just
No?
one, right? Just one.
Yeah. It has 1 neutron or 1. We know it has 1 proton, right? Well, that's all right. It's all right. But you got to cover your cover. Okay. Okay. I'm glad you threw out the guess because you said it was 0.008. So the point is that we can't have a fraction of a neutron. We're not going to have a neutron, right? So we know that the mass of hydrogen is 1, right? It's 1.008. So we have to round to that number. So if we round 1.008, what is it going to equal? Just 1. So if we subtract 1 from that, 0. So hydrogen doesn't have any neutrons. So it has a proton and an electron, but no neutrons. Okay, carbon. Let's look at carbon. Its atomic number is 6. How many protons does it have? It has 6. How many electrons does it have? 6.
6.
Okay, then how many neutrons does it have? 6. How did you figure that out?
12 minus 6 equals 6.
That's right. 12 minus 6 equals 6, right? Piece of cake? Okay, so let's see if you guys really got it or you just want smoking my butt. Okay, so let's take a look at copper. I mean, cobalt, not copper, cobalt. I used copper this morning. So. Okay, cobalt. How many protons do I have?
7.
27. How many neutrons do I have? Are you sure?
27.
Ooh. Okay, we heard 27, 32, 33. That's right, we got to round up. So we have 58.933. So we have to round up to 59, right? So 59 minus 27.
32.
32. So we have 32 neutrons. How many electrons? 27. So 27 electrons. And 27 protons.
So pretty much to get the neutron, you subtract the mass number minus the protons.
That's right.
And then you have the same electrons as you do protons.
That's right.
Okay.
Okay, you guys got that? I'll try one more just for the road. Let's do mercury. Mercury. Okay, mercury. How many protons does mercury have?
80.
Okay. How many electrons does mercury have?
80.
80. And how many neutrons does mercury have?
121.
Mm.
Okay. And we calculated that by,
Subtract the mass with the protons.
so it's 201 minus 80. So 201 minus 80 was what?
121.
121. There you go. Okay. Questions? Concerns? Cash? Okay, piece of cake, right? Not too hard. Okay, so let's see. Let's move forward then. Okay, so have you guys heard of the prefix iso? Isothermic, isotonic, iso. Never? Okay. So what was that? What does it mean in basketball? What 101? So also meaning the same, right? Okay. So iso basically means equal or the same. Okay. So isotope basically means that it's the same element, but it has different masses. Okay. So if it's an isotope, it's the same element, but has different masses. So like, for instance, we have carbon. So we have carbon 12. This here represents the the mass number for carbon. This here is the atomic number for carbon. And so when you see it written like this is called the nuclear symbol, right? And we have carbon 13. Carbon 12 is the most abundant. We have tons and tons of it. And carbon 13 is less abundant. Okay. Now, have you guys heard of carbon dating? Carbon dating. So, DAT. Carbon date. Like, hey, baby, what are you doing tonight? You want to go out on a date? Date. Okay. Yes, exactly. Yes. Okay. So it's not that type of dating, but it is like dating the bones, right? Okay. So carbon dating is basically what's happening is that you're using this isotope. This isotope is rare, right? And it gets incorporated in, let's say, bones or in trees or the longer that they're on this earth, right? So the more carbon 13 you have, the older you are, right? So for instance, you guys are pretty young, so you guys aren't going to have that much carbon 13. But like a redwood tree or something like that that's been out here for thousands and thousands of years is going to have a lot of carbon 13. And so by looking at the amount of carbon 13 in that tree, we can determine the age of that tree, okay? And we can almost determine the age of you. Yes, sir. Yep. Yeah, so that they would find fossils that are there, people's old people bones, right? So they could use that to sit there and determine the age, how old that civilization was. Yes. Yep. Yep, they can do that. That is possible. Okay, so isotopes are the same element, but it weighs differently. So how is it going to weigh differently? We know that the number of protons are the same because that is what defines the element. So then how is it going to weigh differently? Say it again. Are you confident? Yes. So it has something to do with the number of neutrons. So if carbon 12 has 6 neutrons, then carbon 13 must have how many neutrons? 7, right? So an isotope is going to differ by the number of neutrons that we have. Got it? Piece of cake? Okay. So one thing also about isotopes, the ones that are most abundant, they're the ones that are going to be the most stable. The ones that are least abundant, they're not going to be as stable. Okay. So let me give you an example here. Go to P table again.
I'm sorry, can you repeat that? Most abundant?
The more stable it is.
Thank you.
The isotopes that are least abundant, the least stable it is. Okay. So let's take a look. So let me get back to you on that one, okay? Okay, so if we take a look at phosphorus, we go down to P table. At the very bottom, it'll list all of the isotopes for phosphorus. Okay, so phosphorus has 3 isotopes. So we have P31, we have P32, and P33. So most of it is P31. So that means that the bulk of it is phosphorus 31. We have trace elements of P32. And we have trace elements of P33. So those are very, very least abundant. They're not as stable. So they're not going to stick around as much. Okay. Yeah, it basically means that there's so little that is hardly recognizable. Right? That's right. Okay. Okay, so again, when we write our nuclear symbol, the upper number on the left-hand side is called the mass number. You guys know how to calculate the mass number. Or the mass number will now represent the mass of that particular isotope. So carbon 13 weighs 13, where carbon 12 weighs 12. Okay. So if I give you on an exam, what is the mass of carbon 13? 13. Okay. It's not going to be 12. You guys got that? Okay. So the way that we write out the isotope one way is just writing out carbon 12, carbon dash 13. Okay. So what I want you guys to do is, you guys can get in small groups of 4. And then I want you guys to fill out this table. I'm going to add a couple on. 2 more onto this. We're going to do right down my him. $84, mass of 212. Yep, adding one more to it. Okay. It's polonium. Stop making fun of my 3rd grade handwriting there. Okay, so I'm going to put you guys that are online, I'm going to put you guys in breakout rooms. And so we'll give you guys a few minutes. We'll say 5-10 minutes. So are you guys ready? Okay. Let's see what we can do. Okay, so what is the symbol for barium?
BA.
Okay, what is the atomic number?
56.
What is the number of protons?
56.
What is the number of neutrons of this particular isotope?
81.
The number of neutrons is going to be 82 because it's going to be 138, which is this new mass number that's given right here,
130.
minus 56.
Dr. Henry, I have a question about that.
Yes, ma'am.
So okay, so on all of them, like if it has, you know, if it's not like a whole number, you'll always round up rather like how it's 137.33 instead of it just being 137, it's going to be 138 like all the time if there's always a number after the
No.
period.
No, it just depends on which isotope that we're making reference to. So in this
Oh.
case, we're not talking about the periodic table. We're talking about the isotope. And so we look at the nuclear symbol here, what I have circled. Can you guys, let me see. So
Got
this
it.
part here, that's circled, right?
Okay.
So that's the new mass of that isotope. So that isotope weighs 138, where what you guys have on the periodic table, that is 137. And I'll get to
Oh.
that number specifically, why it is greater than a whole number. Okay.
Okay.
Okay. So then the mass number for this is now 138.
Mhm.
And so we would call this guy barium
138.
138.
Got it.
Okay. So the next one, oxygen. What is the symbol for oxygen?
Oh,
What is the atomic number for oxygen?
8.
What is the number of protons for oxygen?
8.
Okay, the mass number is going to be the sum of both the protons plus the neutrons. 18. So the nuclear symbol for this isotope is going to be O, 18 up top, and 8 beneath. And this guy would be called oxygen
18.
18. Okay. The next one. So what element has an atomic number of 82? Lead.
Lead.
There's a question. Hold on. Okay. That's right. PB is the symbol.
Mhm.
Number of protons.
82.
82. Number of neutrons.
124.
Okay. The nuclear symbol.
P 206 over
206. Okay. Oops. Let me fix that.
over 82.
PB 206. And I'm running out of room still. And over 82. Okay. And then this would be lead
206.
206.
206.
Okay. The next one. The element, zinc. Symbol,
ZN.
okay. Atomic number,
Mm, 30.
number of protons,
30.
number of neutrons,
36.
mass number,
66.
nuclear symbol,
66 over 30. ZN.
okay. Last one, symbol, PO, number of protons, number of neutrons,
212 minus 84.
number of neutrons,
128.
okay. Nuclear symbol,
PO.
And 212 over 84.
and the name of the isotope,
Polonium.
polonium 212. That's right.
Mhm.
Sorry, I ran out of room. 12 of them.
I'm sorry. I'm kind of confused though.
Okay.
So you said that these are not from the periodic table, that these are isotopes, but they're elements from the periodic table. So how are they presented differently, if that makes sense?
Okay, so I want you to think about it, right? So
Okay.
do they weigh exactly the same? So like for instance, oxygen. How much does oxygen weigh on the periodic table?
Oxygen is 15.999.
Okay, so 16, right?
Right.
And this one weighs 18. So what is the difference between the isotope of oxygen and the oxygen that's on the periodic table?
Okay. I guess my question is more like where, like I see the weight difference, but where would we find them, I guess? Or do they just, I don't know how to explain what I'm trying to ask.
I think I understand what you're asking. So
Yeah.
you're asking me in real life, where am I going to find these at, right?
Right.
Okay, so in real life, you find them everywhere. So on the periodic table, what you have is a combination of both the isotope and the one that's stable, right? So you
Okay.
have the normal one that is the most stable, and you have the isotope. And all we're doing is taking the average of them all together, and that's how we get the weight on the periodic table. So the reason that we get 16, right, or 15.99999 is because we have the isotope, 3 different isotopes that exist for oxygen. We have one that's going to be 15. We're going to have one that's going to be 16, and we're going to have one that's going to be 18. And they're going to be in different abundance, right?
Mhm.
So let me get to the next slide, and it'll kind of explain this to you a little bit more.
So
Okay.
for
Okay.
barium, would it be barium 138 or just barium?
It'll be 138, barium 138. I ran out of room, sorry.
Mhm.
And I actually have the next slide that I'll actually give you the.
Oh, okay. Cool.
Okay. So okay. So hold on to that thought. So Maria, in a few
Yes.
minutes, I want you to ask the same question, and we'll go over it in a little more detail. Promise.
Okay.
Okay.
Yes.
Promise.
Yes, I promise.
Okay, good. Okay, so now you guys have thought about this, right? You've had time to think about it. We've talked about the lecture. What was the question I asked you at the very beginning? Okay, so we want to know which part of his theory was true and which part of it was crap. Okay, so which part of it was true? Is that true? Is that true? Say it again. Why not? Because we could have isotopes, right? So they can't all be the same, right? Because we have isotopes that exist. We have carbon-13 and we have carbon-12. Both of them exist in nature, right? Okay, so that proves that they're not all identical in every aspect. Okay, what else? The indivisible, okay. So, which is nice read, right? So that basically tells us that we have subatomic particles, right? We could break it down to protons, neutrons, and electrons, and we can change those, right? Because we could have different amount of neutrons. Okay. Okay, so that brings us to the atomic mass. We've been talking about the atomic mass, right? So the atomic mass is based upon carbon-12, the isotope carbon-12. So an atomic mass unit is 1/12 of the mass of the atom carbon-12. Okay, so 1 unit is equal to 1/12 the mass of 1 carbon unit. So everything is based upon carbon-12. That's the take-home message, right? So our periodic table is based upon carbon-12 because that was the one that was that we revolved around. Carbon is going to be very important to us too, right? And so it kind of makes sense that it's based upon carbon-12. All life revolves around carbon, right? Okay, so when we look on the periodic table gives us the average mass, the average atomic mass, okay, of all of the isotopes that exist, okay? So carbon-12, if you look at the weight, it says 12.0011, right? So the majority of it is carbon-12, only a small fraction of it is carbon-13, okay? So let me give you another example. So here we have neon. Neon has 3 isotopes. Now this is a graph that is from a mass spec. Mass spec is an instrument that is able to determine the mass of a particular atom, right? And so it actually will ionize that atom, and then by doing that ionization, you're able to sit there and calculate the mass. Okay, so neon has 3 isotopes. It has neon 20, it has neon 21, and it has neon 22. Neon 20 is the most abundant. Neon 20 is about 90.48% in abundance. Neon 20, neon 20. Neon 21 is 0.27% abundant. And neon 21 and neon 22 is 9.25% abundant. Okay, so let me put this in kind of terms that we understand. If I had 100 neon atoms, 90% of them are going to be neon 20. 9% of them are going to be neon 22. And only 0.27% of them, or you can't have a cutoff, but less than 1 is going to be neon 21. Okay. So if we look at the periodic table, the mass on the periodic table is just the average of all of the neon isotopes. So neon 20, so we go 20, times, we put 90%, that 90.48% into decimal form. So that's 0.9048 plus 21 times 0.0027 plus 22 times 0.0925. Who's quick with the calculator? What was that? It should be 1. Are you sure? Don't put money on it? Got to make money on the side some way, right? So 20 times 0.9048. So this one here is 18.096. 21 times 0.0027. So that's 0.0567. And then 22 times 0.0925. So that's 2.035. So if we add them all together, so we get 20.19. Okay. So if we take a look at the number, it's going to be 20.19. If we look on the periodic table, we get 20.18, give or take. I'm off by a little bit. Okay. So the average that you guys see, the number that you see on the periodic table is just the average of the number of isotopes. Yes, sir. You had a question? Or comment? Yes, it's okay because in most cases, it's rounded. Is he locked out? Okay. Questions? Let's see. There's a chair over here. Okay. Questions, concerns, Cash? Because this is percentage. This is percentage. And so we need to put it in decimal form. Yeah. Okay. Yes. Okay. So Maria, back to Maria's question. So in the real world, all of these guys actually exist, right?
Okay.
And so we're going to have a fraction of each one present. Okay,
Mhm.
make sense? Okay, good. Now, let's see if you guys can do the same thing. So the natural distribution of the isotope of boron is 19.9% of boron 10 at a mass of 10.012937 units and 80.1% of boron 11 at 11.0093055 units. Calculate the atomic mass of boron.
Is it 10?
Is it 10? No, it's not going to be 10. It should be a.
Oh. Wait.
And also pay attention to sig figs, significant figures.
Oh, 15. Sorry. Is that right?
No, I think you want to do a little more math there.
Okay.
Yeah. Okay, so let's go ahead and try to work this out together. Okay, so if we're going to be calculating the mass, the atomic mass of boron, we're taking both isotopes into consideration, right? So we're taking both of them in consideration. We're taking the one that we have 19.9% of. So I'm going to use the decimal for that. So decimal for 19.9 is 0.199. And we're going to multiply that one by the actual mass, which is 10.0212937 plus 0.801 times 11.0093055. Okay, so if we do the math, so how many sig figs should I have? 3 sig figs. So if I have 3 sig figs, that's 1.99 for this guy, plus
8.82.
8.82. And we add these two together.
Equals 10.81.
And that's units. So if you look on your periodic table, what do you guys got? Is it 10.81 for boron? Okay. So, second question, naturally occurring lithium is composed of two isotopes, 7.59% at 6.0151224 units and 92.41% at 7.0160041 units. So we're going to do exactly the same thing. So we have 0.0759 times 6.015 1224 plus 0.9241 times 7.0160041. This guy 0. How many sig figs? 4, 5, 7 plus how many sig figs will we have over here? 4. That's right.
Dr. Henry?
Yep.
The 7.59%, would it be 0.759 instead of 0.0?
It's 0.0759 because we divide this number by 100, right? So then that'll be 1, 2 spots over, right?
Got it.
If you divide it by 100, it's 0.079. Because percentage is just based upon 100, right? So we would just divide that by 100 to make it decimal form.
Thank you.
So we have 1, 2, 1. So that's 6.483. And if we add it together,
$6.94.
so we get 6.94. Oh. Okay. And what do you guys have on your periodic table for lithium? Yeah. Okay. Okay, questions?
Is that a 6.0 or 9?
That's 6.940. Not yet. Sorry. 6.940. Just hold on 1 second and I'll before you go. Okay, questions? No questions? Simple so far? Okay, good. Yeah. So did you guys get 6.94? Oh. Okay. Okay. It's 6.940. Yeah. Yeah, that 0 is for sig figs. So remember sig figs? Yeah. That's right. technically it would be wrong. You would get on an exam, I would give you a -1 point off for that.
For what?
I said on an exam, you would lose, like say if it was worth 5 points, you would lose 1 point for not getting sig figs.
Oh, okay.
Yes, sir.
Wait, what was the final answer? 6.9.
Okay. Total different topic. Remember we talked about that. Okay. Okay. So moving on. So this here is just a table. I'm sorry, you had another question. I'm sorry for
Oh, I saw it was like 6.940, but then it was 6.94
0.
Oh, so that.
Yeah, 40 U. U is the units.
Oh, okay.
So
So
it's yeah.
substitute the O and put a U, or just leave it as a 0. I mean.
No, so the answer would be 6.940 in terms of sig figs.
Yeah.
And then you would put a U for the unit because it's units, right? Because it's atomic mass units, you would use either AMU or just U for the units.
6.94 U for units.
That's right. So the U stands for units.
Oh, okay, got it. So that would be the final answer.
Yes. So you always want to include the units. That's
Okay.
correct.
All right, I'm good.
Okay. Okay. So if you look on this table basically shows you some of the naturally occurring isotopes. And this kind of shows you that, like, for instance, hydrogen has 2 isotopes that are available. One that's at 99.988%, and the other one is at 0.0115%. Both of those exist in nature, right? The only thing, one is much more abundant than the other, okay? So normally I'd have you guys do this calculation, but I'm not going to have you do the calculations because we did 3. We did the neon, we did the lithium, and we did the boron, right? You guys are getting the understanding on how to use it, right? So let's move forward. So you guys can take a look and do this on your own, just to make sure that you got a good understanding, because there's a strong possibility that you'll see this on an exam. Okay. Okay. So the periodic table is organized in a certain fashion. Initially, it was organized based upon the atomic mass. Now that was a hot mess, right? Because we have some atomic mass that don't line up with the atomic number, right? So we have some elements that have a smaller atomic number, but have a much larger atomic mass. So it kind of made things odd. It didn't work out so well. So then what happened over time, we realized that it's best to organize it based upon the number of protons or the atomic number. And that's what we've done. This is the periodic table. You guys know P table, right? So let's talk about the organization of the periodic table. Okay, so we have P table here. So if you look up top, horizontally, these numbers on the horizontal, so those are called groups. Okay, so these up top are groups. These here on the side are called periods. Okay, so elements that are in the same group are going to behave very similar to each other. So for instance, these are all alkali metals down here. These metals are very reactive. They want to react. They want to pop up, right? Any chance they get, they want to pop up. And we'll explain to why they want to do that. These elements over here, these guys are called noble gases. They're noble, right? They don't want to react. They're kind of cool. They're like the cool kids. They just kind of sit back and let everybody envy them, right? They got everything that they need. And we'll talk about that here in a second too. Okay. These guys here in group 17, these guys are called halogens. They also want to pop up. They're very reactive, right? So they want to react with just about anything. And we'll talk why that's the case here in a second. Okay. So the periodic tables is organized in a very specific manner. On the periodic table, we have metals, we have non-metals. If you look on P table,
Mom, you want to see?
click up here, it'll highlight all of the metals.
Mommy, I found.
We also have a group that are called metalloids. Metalloids have characteristics of metals, and it also have characteristics of non-metals. Okay, so they're kind of in the middle. They kind of swing both ways. And then we have non-metals. These are all the non-metals. Okay,
Love you.
so
Nana.
often when we're trying to find things on a periodic table, we have to use those groups and periods. Like for instance, if I'm in period 3, group 16, what element is that? Sulfur. Okay. If I'm in period 6, group number 7. Rhenium. Okay. Okay. Piece of cake. Okay. So in the old days, when I started chemistry, we had things broken up in what we call the main group, and we had a minor group. The main group would be groups 1 and 2, and then group 13 through 18. Now, if you count this, there's 1, 2, 3, 4, 5, 6, 7, 8 groups in the main group. The reason why the main group was used is because it was based upon the octet being full. It was also based upon the fact that transitional metals, although we knew about them, we knew that they react, we didn't quite have a good grasp on some of the aspects of how they react, right? We know that now, so we don't separate them as much, right? But you'll still see some periodic tables that will have a main group and a minor group. If in those cases, they would label this one as A1 through A8. A8. Sorry, that's a horrible A. 1 through A8. So it would be A's, meaning the main group, and B's would be our minor group. Okay? And so sometimes you'll see that, or sometimes they'll say, oh, 1A. You'll see it written both ways. Okay? Questions? Concerns?
I'm sorry, what's the one going down? The one
These are periods,
periods?
periods,
Periods and groups.
periods and groups. That's correct.
Okay, thank you.
Okay. Okay. So we go on our periodic table. Periods. We talked about what periods are, and we've also talked about groups. We also talked about elements that are in the same groups are going to behave very similarly. Okay. Oh yeah, I did learn chemistry back then. Yep, things have changed quite a bit. We'll put it like that. So, and it's always changing. That's the best thing about science. If it's not changing, it's not science. Sir. Okay. So we've talked about metals, we talked about non-metals, and we talked about metalloids. You know how to find them, right? You guys can use your periodic table to sit there and find them, right?
Mhm.
So give me an example of a metalloid. Metalloid.
Silico?
Okay. Perfect. So on your periodic table, the beauty is that in the small part of your periodic table, there is a small letter on the side. It'll let you know what it is. And then in that case, it has metalloids or metals. Yeah. Okay. So let's get started. Let's give you guys some little more information, right? You guys already did this, right? Piece of cake. Now let's give you guys more information about the periodic table, right? Let me go back to the periodic table. Okay, so these guys, I told you pop off, right? So they react almost instantaneous. Now let me tell you the reason why that they do that. So everybody wants to be like the noble gases. What does noble mean to you? High class, fancy, right? Okay, so everybody wants to be like the noble gases. So on the periodic table, if you're not a noble gas, you're trying to find a way of being like a noble gas. Now, the way that you become like a noble gas, there's three ways that you can do it. One way is to give up electrons. One way is to take electrons. Or the last way is to share electrons. Okay, so it's about give, take, or share. Kind of like life, right? Life's about give, take, or share, right? Either you're giving, or you're taking, or you're sharing, right? Okay, so the elements are going to be very much like you in many ways. The other thing is it's also about energy, right? Now, I'm going to ask you this. Now, I want you to think real hard on it. If you had to mow 5 lawns and make $500, or you can mow 1 lawn, that's about the same of each of those 5 lawns, and make $500, which one are you going to do?
The
What was
one
that?
lawn.
I'm going to do the 1 lawn for $500, right? Okay. So why would you do that? What's the rationale? Say it again. Less work, right? Less energy, right? So less, and so it's all about the energy. Okay, now this is going to be all about the energy. So the reason that these other elements want to be like the noble gas, because it's less energy to be like the noble gas. Not only you're cool, everything is given to you, you're good to go, right? And it's less work. Man, win-win, right? Okay, so when we think about this, we've got to think about them trying to use the least amount of energy as possible, okay? So they're going to try to find a way of getting to be like a noble gas, right? So these metals are basically one away from being a noble gas. If they lose 1 electron, they'll be just like a noble gas, right? So losing 1 electron will make them just like a noble gas, right? Or they have the option of gaining 1, 2, 3, 4, 5, 6, 7 electrons. Now, think about it. If you had to walk 1 block to this store that's exactly the same as another block that's another store that's 7 blocks away, which one are you going to do? You're going to walk the 1 block rather than walking the 7, right? So it makes sense. The electrons, I mean, that atom is going to do exactly the same thing. Now, if it loses 1 electron, then what is going to be the overall charge on that element? It's going to be positive. Why? It lost 1 electron, right? So if it lost 1 electron, let's say, for instance, if we're talking about lithium, lithium has a total of how many electrons normally? It has 3 electrons. So I'm going to put 3 E minus. How many protons does it have? 3. So the overall charge on it right now is neutral. So if I lose 1 electron, then I have 2 electrons, and I have 3 protons. So the overall charge is going to be positive. So the way that we would represent that is Li plus. Okay, so this is called an ion. Ions are charged elements or charged particles, right? So if it's positively charged, it's called a cation. People will also call it a cation because it's positive. A cation because it's positive. Okay. Finally, somebody laughed at my joke. It took me like 5 times to say it this week for somebody to laugh at my horrible joke. Okay. So I'm feeling a little love now. Okay. So if it's positive, it's a cation. Now, the halogens are 1 away from being a noble gas. If they gain 1 electron, then they're going to be just like a noble gas. So fluorine, if it gains 1 electron, it'll be like neon. So then that means fluorine gaining 1 electron is going to have a negative charge. Okay. Yes, ma'am. cations are positive, anions are negative. Okay, they're both called ions. Ions is the general group. Either you have a cation or you have an anion. Now this guy is an anion because it's negative.
So what would you put for like the one under like bromine or bromine, for example?
Bromine.
Yeah.
So if it's bromine, so bromine down here, how far is it away from being a noble gas?
One. Is it right over?
One away. That's right. So if it's one away, if it gains that one electron, it just becomes Br minus.
Br negative.
That's right. Okay. Now oxygen. Oxygen is how far from being a noble gas? Are you
2.
sure?
Negative 2.
It's 2. 1, 2. So then the charge on that is going to be 2 minus. So we'd write it as
O2 and then
2 minus. Okay. Calcium. Calcium is 2 away. If we lose 2, 1, 2, it will be like neon. So what's going to be the charge on calcium? Ca2 plus. So calcium is here. It's 2 away from being a noble gas. Here, 1, 2. It wants to be like these pink guys over here, right? So then it's going to lose 2 electrons to be like a noble gas. Yep, you count backwards. Okay. On this side, yeah, on this side you count backwards. So there's like this breaking point, and we'll talk about this in a second, right? We also have, we'll talk about it now. So we have carbon. Carbon has the ability to be like a noble gas by either adding 4, 1, 2, 3, 4, or losing 4, 1, 2, 3, 4. So carbon can swing both ways. It can lose 4 or it can gain 4, right? So if it loses 4, it's going to have
+2.
If it loses 4, it's going to be
4.
plus what? Plus
5.
4.
Wait.
If it loses 4 electrons, it's going to be plus 4. If it gains 4 electrons, it's going to be minus 4. Yeah, so it would have to go this way. 1, 2, 3, 4, right? And then if it loses 4, it goes the other way. 1, 2, 3, 4. Right? So it's like right there in the middle. So it can go either way. Now this is very beautiful. Remember carbon center of life, right? So that means that carbon can gain 4 electrons or it can lose 4 electrons. Okay? So carbon has the ability of going both ways. Carbon also has the ability of having 4 attachments. It can have 4 bonds too, right? So that's what makes it so sexy. It also makes carbon a little bit of a whore. Carbon likes to make everybody happy. Either I could go this way or I could go that way, right? Okay. So let's watch a quick video. It's NC7. I said it's NC13, isn't it? Not NC13. PG13. You're okay.
Wait, could you also do like for carbon like C to negative?
No, so carbon is only going to be like a noble gas. It either is going to gain 4 or it's going to lose 4, right? It's only going to be, it won't be C2 negative, right? Oxygen will be O2 negative because it's only 2 away from being a noble gas. Does that make sense?
So when do you have that breaking point where?
Whether you gain or lose,
Yes.
it really just depends on where you're located at, right? So like for instance, boron, you want to use the least amount of energy, right?
Okay.
So
Okay.
boron is here, right? You see where boron is located at?
Yes.
So you have the option of gaining 1, 2, 3,
5.
4, 5, right? Or if you lose 3, 1, 2, 3. Now, if you're walking, there's a store that's 3 blocks away or a store that's 5 blocks away. Which one would you go to?
3 blocks away.
Right? So the atom is going to do exactly the same thing. It's going to find the lowest way, the cheapest way to get there, right? Because it doesn't want to waste that energy. So it's going to go that 3 blocks away. So it's going to go 3. So in that case, it's going to lose 3 electrons to be like helium. Okay?
Okay.
Does that make sense, Lucy?
Yes, I got it. Thank you.
And I can't remember who else was talking.
I think Jason was.
Was it Jason?
Yeah. I don't know. I'm
Does
just
that make sense?
like a little bit like I understand that, but if you
It's going to take a minute.
different one, I'd probably be confused.
Okay. So let me show you guys a quick video. Yeah, this was not working at all.
Can't get it now. I can't get it now, but I can get it. Can't get it now. I can't get it now, but I can get it. Walked up the stairs. Walked up the stairs. Can't get it now. I can't get it now. I can't get it now, 'cause the pocket's downstairs are going to quit. The pocket's downstairs are going to quit. I can't get it now, I can't get it. I can't get it now, but I can get it. Can't get it now. Can't get it now, but I can get it. Can't get it now, but I can get it. I walked up 2 flats.
Okay. So, can you guys hear me? On the other side, can you guys hear me?
Yeah.
Okay. So, noble gases, they're not going to want to react because they're stable. They're all set. They're good to go, right? So, carbon is able to sit there and interact. It has the ability to sit there and have 4 attachments, right? It's going to try to make whoever it's attached to kind of happy. Oh, you need an electron? Oh, yeah, I got an electron for you, right? Okay. So, it's important for us to understand that in terms of the chemicals are going to try to use the least amount of energy. We saw that lithium and water, or was it potassium? Potassium and water, right? Volatile, right? Reacts like that. Okay. So they're going to try to use the least amount of energy to try to get stable. Lithium, potassium, group 1 metals, all of those guys are very reactive. They're like, oh, they're quick to pop off, right? They want to react immediately with water, right? Because they want to get rid of that electron. Once they get rid of that electron, they become stable because they're like the noble gases. Okay? You guys good? Okay, so let's go. Now let's talk about those charges, right? P table. So if I have potassium is going to have what charge associated with it?
Positive.
Potassium. So if it's an ion, if it forms an ion, what type of ion is it going to form? Are you sure? Okay, how many of you guys say negative? Raise your hand. How many of you guys say positive? Raise your hand. Okay. So potassium is located here, so we know that it's going to form K plus, right? Okay, now that means it lost an electron. Now, if it does that around fluorine, fluorine's going to pick up that electron, and it's going to become F minus. Okay, because fluorine only needs one electron to be like a noble gas. Now, these guys, you have a positive and a negative, kind of like us in our relationships, right? We always want to go for that positive or negative person, depending on what you are. So a positive is going to attract a negative. So these guys are going to come together, and they're going to form potassium fluoride. You notice that when they come together, there's no charges associated with it because they balance each other out. Yes, sir. Yes, it can, but calcium is going to need 2 fluorines to balance it out because calcium has what charge associated with it? Not just a positive, it's how many away from being a noble gas? 2, so then it's going to be what? Ca 2 plus. So then how many fluorines am I going to need to balance it out? I'm going to need 2 fluorines because each one is a -1. So in this case, this guy would be called calcium fluoride. Okay. That's right. So this is called ionic bonding. Okay. Why do you think it's called ionic bonding? Because we have 2 ions that are coming together, right? Now, ionic bonding occurs typically between a metal and a non-metal when we're talking about monoatomic ions, a metal and a non-metal. Metal, non-metal. Okay. Now, I want you guys to think about this. Give it thought. Okay. Now I'm going to pose a question to you, and I want you to think. Now, I know that nobody in here is a criminal or anything like that, but if you were a criminal, right? If you were a criminal, would you steal from your neighbor or would you steal from somebody across town? Or, okay. What was that? Oh, you think so, huh? He would recognize that his bike that you just took, right, and riding it down the street. Okay. Okay, so most of us who have common sense would actually take from the person across town, right? Okay, so when we're taking and giving, it's going to be with the metal. But your neighbor, you're more likely to say, even though you may use it a lot more, you're going to say to your neighbor, hey dude, let me borrow your bike, right? And you just take it for the whole day, right? Okay, so in that case, you're going to share with your neighbor, but you're going to take from the guy across town. Okay, so that's kind of what's happening. The metals are over here, the non-metals are over here. So you take from these guys, right? But if he's your neighbor, you're going to share. Now, sharing electrons is called covalent bonding. Now, how many of you guys have siblings? Are you the older sibling or the younger sibling? Oldest? Oh yeah, you guys can relate to me then. So I'm the oldest sibling, right? I come from a very poor family. So during Christmas, typically we get underwear, socks, shirts, things that you have to have. And then we would get a gift to share, right? And so when I was growing up, we had the Atari. You guys have the PlayStation 5. I was told it's 5. It's not 7, right? Okay, so PlayStation 5, that's the new one. Okay, so it's kind of like getting a PlayStation 5 for you and your brothers and sisters, right? So I got the Atari, right? And, or I should say, we got the Atari. And my mom says, you got to share, right? So I'm the oldest, right? My mom worked almost all day. So like on the weekends and stuff, my dad was on the boat, right? So he was never around. So weekends would happen, and the rule was that I was responsible for, keeping my sisters in check during that time period. And then around dinner time, I cook dinner, and my mom comes home, she'd eat, and then she'd go to her next job. That's the way it worked, right? So typically what happened was I played the Atari all the way up to the point that my mom's getting ready to come home, right? And then it'll be like an hour before my mom comes home, so I get in there and I cook. And then like 30 minutes till like she got there and everything, we get together and we eat. And then I get on the Atari again. So, but during that time period, my sisters got to play. So for about an hour and a half, my sisters got to play, but the whole day I got to play, right? Now that's sharing, right? Isn't it sharing, right? And being the older brother, I kind of got the system worked out. Now, is it even sharing or fair sharing? So that concept is also what happens in the case of elements. So like for instance, water. Water is actually hydrogen and oxygen sharing. Now the electrons are going to spend more time around the oxygen than the hydrogen. Putting these dots here, which represent valence electrons. They show. Okay, this line here represents sharing, a covalent bond. So they're actually sharing those electrons. Now, really what happens is that the electrons spend more time around oxygen than they spend around hydrogen, because oxygen is kind of like the big brother. He's like, it's mine, it's mine, it's mine, but you could have it some of the time, right? Okay, so that's uneven sharing, or we would call that polar covalent bonding. Okay, so polar covalent bonding is uneven sharing. Okay, non-polar covalent bonding is even sharing.
Where's pumpkin?
Okay, how you guys doing? Good? Good? Okay. Okay, so ionic bonding is what? It's between a metal and a non-metal, and it's also based on positive charge and negative charge. So it's give and take. So that's an example of that give and take. One is giving up the electron, one is taking the electron. We all have relationships like that, right? So, he's going to dig himself in a hole. Okay. Okay, so ionic bonding is that give and take, and then covalent bonding is sharing. Okay. Let's go back to the slideshow. Okay, so you guys are very familiar with the elements so far. So these are the most common elements that we're going to be talking about. Over time, you're going to know them, and you're just going to kind of know them because you've interacted with them on the periodic table. I don't expect you guys to memorize, right? That's why I gave you guys the periodic table, and you'll have that for the exams. Some instructors believe that you should memorize them. I don't think you should. I think it's a waste of time. There are other things that I want you to know. Okay, so with that, we're going to take a 5-minute stretch your legs, go potty, go get a drink of water, go to your car, drink that beer. No, I'm joking. Kid, I kid. Okay, and then we're going to come back and we're going to start chapter 6. Okay. Okay. So we're back. Everybody's back. You guys are ready? You got your energy back up. You got your stretching in. You guys are ready. It's gonna be exciting. Okay. Let's go. Let's go. Okay. So we've talked about, we're going to talk about chemical formulas. So often we have what we call the subscript. You guys, we talked about this earlier. You guys remember when we talked about the subscript? The subscript denotes what? What does it tell us? What was that? How many? How many of what it's right next to, right? In this case, we have 2 hydrogens here. And if there's no number there, we know that it's understood to be 1. So there's 2 hydrogens and 1 oxygen in water, right? Here we have sodium chloride. That means we have 1 sodium, 1 chloride. Okay. Now, we know, because I just talked to you guys about it, this here is an ionic compound. This here is a covalent compound. Okay. Now, the way that we go about naming these, we're going to be different. Water, we always call water. That's a traditional name. We're not going to change that name. We're not going to call it dihydrogen oxide, right? We're just going to call it water because that's what we know it is, water. Sodium chloride, sodium and chloride. Sodium is the metal, and it's going to be that ion. And then chloride is from chlorine. So we use the I to let us know that it is a negative ion. It's also letting us know that it is the end of that compound. First part is sodium, second part is chloride. We always put the metal first in ionic compounds, or the cation first, and we put the negative ion second. So the way that I typically know that people are using Google on exams is that when they put it in there, sometimes they'll end up putting chloride sodium, because a lot of times Google put it in the wrong order, or somebody on Google wrote it wrong. Sometimes that's me, right? So some of the information on there on Google is incorrect. Okay, so we've talked about diatomics. Have we not talked about diatomics? Okay, can you tell me the 7 diatomics? Oh, wait, first off, how many diatomics are there? 7. Okay, what are the 7 diatomic elements? What's that? You just put it away. Hydrogen. Okay, so we have hydrogen. Carbon is not one of them. So we have hydrogen. We have N2, which is nitrogen. O2, which is oxygen. We have fluorine. That's right. F2. Cl2. That's right. Chlorine. Bromine. And iodine. So those are all diatomic elements. Okay, di meaning 2 atoms, 2 atoms, diatomic, right? So these are diatomic elements. So these are your diatomic elements. Okay, so when they're by themselves, they're going to be written as diatomic elements. So these are the 7. 1, 2, 3, 4, 5, 6, 7. Have no fear of ice cold beer. Remember that? Okay. Okay. So write the chemical formulas for chlorine, argon, bromine, and krypton. Okay. Let's see. So chlorine. Cl2. Argon. Bromine. Br2, that's right. Krypton. Piece of cake? Good. Okay, so we talked about metalloids. We talked about metals, right? You guys know how to find them? Okay. So when we're talking about naming compounds, we basically have what we call a binary system, right? So for the most part, most compounds that we're going to be working with fall into that binary system. So binary meaning two. So you have a first name and then that last name, like sodium chloride or carbon dioxide. Okay. So there are a couple elements that are always going to be traditional elements. We're always going to call them by certain names, like water, H2O, water, ammonia, NH3. Okay. So those are ones that you got to know, right? Those two. Okay. So when we're talking about elements that are covalently bonded, right? So covalently bonded things are going to be things that are all non-metals. So for instance, let's see. CO2. So this guy is called carbon dioxide. If it's CO, it's called carbon monoxide. Okay, so this here and this here, these are called Greek prefixes. So these are the prefixes that are used for one, mono, for two, di, for three, tri, for four, tetra, for five, penta, for six, hexa, for seven, hepta, for eight, octa, for nine, nona, for 10, deca, for 11, deca, for 12, dodeca, for 13, trideca. Okay. What was that? Yeah, in this class, yes. Yeah, if we're in OChem, that'll be totally different. Yeah. You're fine. It's gonna be great. Don't worry. Don't worry. It's all good. Okay, so we use these prefixes to let us know how many when we're talking about covalent bonds, only when we're talking about covalent bonds. So that consists of all non-metals, right? So we have all non-metals together. We use the Greek prefixes to let us know how many we have of each one. So like when we said carbon dioxide, well, it's one carbon, and then we put dioxide, that means two oxygens, right? So what would I name this guy? So it would be nitrogen trioxide. What was that? That's right. Yes, it's the following. Yeah, so the number follows the element that it's representing. So there's three oxygens, right? Nitrogen trioxide. Okay. So how would I write carbon decafluoride? C5F10. Okay. So you'll notice here we have an ide. Now this isn't an ion. Here the ide is just letting us know that that's the end of that compound. So this compound only consists of carbon and fluoride. Fluorine. Right? Okay. Okay, so write the for each below, write the formula or the name. So what would be the formula of dinitrogen pentasulfide? The answer's already there. I know, but you can tell me still, right? Without looking at it. You're not looking at the answer. N2S5. So remind me next semester, all the answers. Okay. Okay, dinitrogen pentaoxide. What is that gonna? Okay, 4 iodine or I4O9. What is that going to be called? This is going to be called tetra iodide. You still need to put the IO. Yep. Iodine. And then, oops, I misspelled that. Nona oxide. Now you'll notice with the oxygen, since you have the oxygen, we drop that A. So if there's an A at the end of it, we drop it, right? And so if we write mono, it's MO monoxide. It's MONOXIDE. We don't have monoxide. You understand? So it's not a double O. So we'll drop the A and we'll drop the O. So for oxygen, okay. So what about the PF5? Okay. So phosphorus pentafluoride. Penta for 5. Okay, got it? Piece of cake? Okay, we've already talked about ions. So monatomic ions, mono meaning one atom. So monatomic ions, either they're going to be cations, which are going to be positive ions, or anions, if it's going to be a negative ion. Okay. So we've talked about those charges and how we get those charges. Right. Now we didn't talk about the transitional metals, right? Because the transitional metals are a hot mess. Transition basically means change. So they're going to be able to change their charges. Okay. And we'll talk about that here in a second. Okay. So this is where I stopped with the other class. Yeah, this is where I stopped with the other class. So we'll start talking about those transitional metals when you guys get back. So this is going to be our breaking point. So reminder, next week on Monday, your exam is going to open up and your practice exam is going to open up. So you have the whole week to do your practice exam. You can do your practice exam 50 times if you want to do it, right? But you want to make sure you get your exam done and make sure you give yourself enough time to do the exam. Okay. Yes, there will be a lab this Thursday for Walinga. Parnell, your lab will be Friday. Fireball, your lab is Thursday as well. You can either do it on a Monday or Wednesday. Yeah, during the day, or you can come in the evening and set it up for tomorrow. Yeah, on a Monday or Wednesday. Yeah. Okay. Yes. So it will open up. So you have the entire week. Okay. And yeah, did we give you chapters 3 and chapter? Oh yeah. Wait, okay. So hold on 1 second so we can get you in. So give me 1 second to get these guys taken care of and done. Okay. Do you guys have any questions?
No.
No questions? Okay. So then I will see you guys on Friday. Most of you guys on Friday.
Thank you, Dr. Henry.
Okay. You guys have a good day.
Thank you. Likewise.
Good night.